today I'm going to talk about the new formula for the effective degrees of freedom for some penalized estimator, including lasso, fused lasso, and slope. Okay. Wait a minute. So this talk is based on the paper I just published last year from Journal Multivariate Analysis. Okay. So here's today's agenda. So just to get into it, so in this talk, I'm gonna think about a linear model like y equals to x theta plus epsilon, where x is a design matrix, n times the design matrix, and the epsilon is a Gaussian noise. And here, I want to assume the noise is Gaussian because of some technical reasons, but maybe I will explain later. And I want to focus on a class of convex regularization estimators defined like this. So that is theta hat estimator is defined as the minimizer of the objective function, which is defined as the sum of the square laws and the convex penalty function omega. So the lasso, in the case of lasso, omega is a L1 norm, right? But this formulation contains another commonly used estimators like fused lasso, group lasso, and slope. So I guess the topic of this conference is about slope, right? And the goal of this talk is to derive an unbiased estimate of the risk. Here, I mean the risk is the mean squared loss of the regression fit x theta, right? And risk can be decomposed into a way like bias variance decomposition. So here the equation of the decomposition. By the way, can you see the cursor on the screen?
Yes.
Great.
We can see the cursor.
Thank you. And so in this equation, the non-trivial part of the risk is DF. So this is called the degrees of freedom. So which is the main topic of this talk. So in this talk, I will derive some simple and closed form formula for degrees of freedom for a class of structured sparsity regularizers, which I call submodular regularization. And this formula contains some new result for some estimators like slope and nearly-isotonic regression and so on. Right. So I'm going to explain some basics of degrees of freedom. So as I said in the previous slide, the non-trivial part in the risk decomposition is called the degrees of freedom. So formally, this is defined as the population covariance between the target variable y and a regression fit x theta hat, right? And this can be interpreted as the effective numbers of parameters in the penalized estimator. For example, use our ordinary linear regression, then the degrees of freedom will be the number of covariates, right? And it has several statistical applications like model selection criteria, such as model CP type criteria, or the biased version of confidence intervals. This is a recent theoretical result. And the point is that we cannot observe the true value of the degrees of freedom directly because it contains the population covariance, right? But we have the unbiased estimate of the degrees of freedom when the expected mean is differentiable with respect to target variable y. So we have a unbiased estimate of the DF hat, which is giving us the divergence of the Jacobian trace of the X theta hat. Okay, so to derive this, we need Stein's lemma. So if you're interested in the detail, please see the paper of Efrons. Okay, so I'm going to introduce some existing result of degrees of freedom formula. So first one is the lasso. So let's say the design matrix is full rank. That means the rank of X is the same as the number of columns of X, right? So in this case, the degrees of freedom of lasso is given as the number of non-zero elements in the coefficient, right? So this is very simple because once we obtain the lasso solution, then we can calculate the degrees of freedom by just counting the non-zero values. And for general X, including some high dimensional cases, then the degrees of freedom is the rank of a submatrix that corresponds to non-zero coefficient. So this is again very easy. And this result is proved by Tibshani and Taylor. Okay. And the second example is fused lasso. The fused lasso is the estimator that is defined as this equation. So here the omega of fused lasso is the total variation of some graph structure. So for example, let's say you wanna eliminate the noise of the two-dimensional image, then the graph structure should be a grid graph like this. And then after we apply fused lasso, you will get some smoother version of the original image. Okay. And the fused lasso tends to be piecewise constant. I mean, the solution of fused lasso tend to be separated into several partitions where the single partition have the same value of coefficient. Okay. So the degrees of freedom in this case is given as the number of pieces. So so in this case, again, the implementation is very easy because we just saw the coefficient in, let's say, ascending order, and then count the number of steps or jumps. So the point is that this degrees of freedom formula does not depend on the graph structure we used. I mean, so that we always count the number of distinct values whenever we use a let's say one-dimensional grid or two-dimensional grid or general dimensional grid or general random graphs. So this does not depend on the graph structure. Okay. So then I will introduce some new result of degrees of freedom formula. So I have introduced two results regarding lasso and fused lasso. So how about slope? Okay. The slope is defined as the estimator penalized by the sorted L1 norm. The sorted L1 norm is, as you know, the weighted sum of the sorted version of the absolute value of data. So here the W is a sequence of decreasing positive weights, right? And regarding the difference between lasso, the norm ball of slope has more vertices than that of the L1 norm. For example, in 2-dimension, the L1 norm ball looks like square. On the other hand, the slope norm ball looks like octagon, right? And the solution of slope will be sparse. So this is the same property as the lasso. But the question is whether we can apply the lasso type degrees of freedom formula to the slope solutions. So in other words, we are interested in the whether the number of non-zero elements gives an unbiased estimate of the degrees of freedom for the slope solutions. Okay, but the answer is no. So because the if we apply the lasso type formula to slope solutions, then we will overestimate the value of the degrees of freedom. Okay, so here's why. Here's an intuitive reason why the lasso type formula failed to estimate the slope degrees of freedom. So first of all, the slope solution becomes piecewise constant due to the extra vertices appearing in the octagon, right? So because of this, the effective degrees of freedom should be much smaller than the number of non-zero coefficients. So here the revised version of the degrees of freedom formula for slope. Okay. So let's say X is full rank. Okay. Then the number of non-zero distinct values in absolute values in theta hat becomes an unbiased estimate of the degrees of freedom of slope. Okay. So this is always smaller than the non-zero, just counting non-zero values like us in lasso. And the implementation of this formula is very easy because you can just solve the absolute values and count the number of jumps. Okay, so here is the artificial example of a lasso solution. So once we obtain the slope solution, then we take absolute value of theta hat, and then after we solve the absolute values, sum of coordinate becomes exactly 0. So the degrees of freedom is the number of steps of the remaining part. So in this example, the degrees of freedom is 5. And actually, this formula comes from a more general result that can be applied to more general penalty, which we call submodular norm regularization, and more general X, including high-dimensional cases. So here's a numerical example of degrees of freedom formula. So here I just generated some artificial data from a Gaussian linear model. And then we apply two types of degrees of freedom formula to slope solution. So one is the lasso type formula, but we can find that the lasso type formula tend to overestimate the true degrees of freedom. Or I forget to explain that the dash black line is the true degrees of freedom formula. And the point is that we cannot observe in practice because the true degrees of freedom requires the true value of the parameter, right? And on the other hand, our formula plotted as green markers seems to estimate the true degrees of freedom correctly. Okay. So here's the list summarizing the some degrees of freedom formula. And as I said before, the degrees of freedom of lasso is given as the number of non-zero values. But I'd like to add some more to result related to this result. So the degrees of freedom of slope and a particular version of group lasso are also given us the number of non-zero distinct absolute values. Okay. And the degrees of freedom of fused lasso is given us a number of distinct values. But this particular formula can be applied to other kind of estimators, such as isotonic regression and nearly isotonic regression, or general d-dimensional isotonic regression. Okay. So these formula are very simple, and do not depend on the underlying structure of omega. So this is a bit surprising, but I want to generalize this result to more general class of penalty function. So the first three estimators will be instances of what I call submodular norm regularization. And the latter three estimators, Fused Lasso, isotonic regression, and nearly-isotonic regression, will be instances of low-Earth extension regularization. So I will explain these things from now. Okay. So what time is it? Okay. So I will explain the main theorem. Okay, so to explain the main theorem, I have to introduce some notion of submodular function. Okay, so let's say we have a finite set V, which correspond to the indices of the parameters. So in this case, we have p-dimensional parameters. So the finite set will be 1 to 2p, right? Okay. And a function f that takes a subset of v and that outputs the real value is called submodular if it satisfies this inequality for all subset AB. Okay, so to understand this inequality, so let's say when you go to a hamburger store, then you may get a discount when you pay for the union set compared to individual menus, right? Okay. And the submodular functions are important function class in combinatorial observation literature. So if you are interested in, please see these textbooks. Okay. And I will introduce another concept, important concept, low-Earth extension. So low-Earth extension of a submodular function is a continuous function f hat defined as this little bit complicated equation. Okay, so this looks like a little bit complicated, but the important thing is that the low-Earth extension is a continuous relaxation of f with some nice properties. Okay, for example, so we can embed the subset of V to Euclidean space by considering a binary sequence, like for example 0, 0, 1, 0, 0, etc. And so the value of Lova's extension at characteristic function of A coincides with the value of the original submodular function. So this means that the f hat is a continuous relaxation of f. And other important property is that the Lova's extension is convex if and only if the original function is submodular. And the Lova's function is a support function of a particular polyhedron defined later. So I'm not sure I have a time to explain this, but this is particularly important for us to derive degrees of freedom. Okay, so I will give some example of Lova's extensions. So first example is set cardinality, which is a function that count the number of elements in a given subset. Then the Lova's extension will be the sum of coordinates. So the point is that we can obtain a L1 norm by passing the absolute value of theta to this Lova's extension. And the second example is a function of set cardinality. So let's say we have a submodular function that is defined as the g of cardinality function. Here, g is a one-dimensional concave function. And by this formulation, we will eventually get something like sorted L1, no? So this is very closely related to slope. And the third example is a cut function of graph. So suppose that we have a graph G, which is either undirected or directed. Either one is okay. And then the cut function of this graph is defined as the number of edges leaving from given subset A. Okay. And then the lowest extension of the cut function is given as this equation. So we can see that if G is undirected graph, then the lowest extension of the cut function will be the penalty function of the fused lasso. And if the G is directed graph, then the lowest extension will be the penalty function of nearly-isotonic regression. Okay, so now we define the two classes of convex regularization, which we call submodular regularization. And in particular, the first class is lowest extension regularization, whose omega is given as the lowest extension. So this class contains the fused lasso and the nearly-isotonic regression, or some sort of hypergraph total variation, and so on. And the second class is submodular norm regularization. So here we assume that the underlying submodular function is monotone in the sense that this inequality holds. And then the omega of this class of regularization estimator is what is obtained by passing absolute values to the lowest extension of the submodular function. So this class contains lasso, slope, and particular version of group lasso, and so on. Okay. So let me comment on some history of submodular regularization. So submodular regularization was introduced in several previous papers, including these literatures. And originally, it is introduced to model some structural sparsity. So fused lasso with some complicated graph structure, or some overlapping group lasso, and so on. Okay. So and submodular regularization has a very good computational property. That is, the following optimization problem can be always solved in polynomial time. So this is a proximal operator of the lowest extension. Okay. So to solve the submodular regularization estimator like this, so we can use proximal gradient method for some common lowest extensions, right? Okay. So here is the main theorem of this paper. So in this talk, we assume that the rank of X is P. Okay, so this is full rank X. So actually, we can also consider any X containing low rank or high dimensional cases. But here I just assume the full rank for simplicity of the exposition of the theorem. Okay. So here the main theorem. So first, for any lower extension regularization, the degrees of freedom is given as the number of distinct values in theta hat. Okay. The second, for any submodular norm regularization estimator, the number of non-zero distinct values in absolute values in theta hat gives an unbiased estimate of the degrees of freedom. Okay, so I think these are super easy, because once we obtain the estimate of theta hat, then we can calculate the degrees of freedom for almost freely, because we don't need any information of the underlying submodular function and design matrix. Okay. So okay. So finally, I will explain some proof ideas. Okay. So proof is basically done by these 3 steps. Okay. And the first step is to represent penalized estimator in sort of dual form. Okay. So first, penalized estimators can be understood as anti-projection estimator. That means the regression fit x theta hat is the residual from the orthogonal projection of y onto some convex polyhedron C. So like this, okay? And the second step is that the divergence of x theta hat is given by the dimensionality of the face containing the projected point, okay? So for example, in this figure, so let's say the polyhedron is this hexagon, and y is the this y is here, and then the divergence of the regression fit is given by the co-dimension of the face dimension. So in this example, the divergence will be 1 because the hexagon is 2-dimensional polytope embedded in the 3-dimensional space. So the co-dimension is 1. And finally, we will derive more simple formula for the using the submodular function. So for the first extension regularization, the polyhedron C is related to the base polyhedron BF associated with submodular function. So I'm not sure I have time to define this polytope. This is a very important concept in submodular analysis. And using some combinatorial structure of the base polyhedron, we can show that the phase dimension coincide with the number of distinct values in the estimator. Okay. So roughly speaking, the first part uses the property from convex analysis, that is KKT condition, support function, or duality. And the second part is due to some geometrical property of the projection map. So, and the final part, we use some combinatorial aspect of the submodular regularization. So we use some theory of distributive lattice or so-called greedy algorithm to show the final exposition of the theorem. Okay. Okay, so I spent almost 30 minutes, so I will summarize this talk. So in this paper, I derived new degrees of freedom formula for wide class of polyhedral convex regularization, which I call submodular regularization. And the formula is easily implemented because we just count the number of distinct variables in the solution. And the formula is also independent of the choice of the underlying structure of the regularization function or the design matrix. Okay. And this formula contains some new result. For example, slope, nearly-isotonic regression, hypergraph total evaluation, and so on. Okay. So that's it. Thank you for listening.